So here's something worth sitting with for a moment. Right now, wherever you are, probably lying in the dark, maybe your eyes are already closed. There are about 100 billion galaxies out there, each one stuffed with 100 billion stars, and every single one of those stars is doing the exact same thing, converting matter into energy according to rules that were set down in the first fraction of a second after everything began. The same rules everywhere, no exceptions anyone has ever found. And those rules, the ones governing a star burning 50 million light years away, are the same ones keeping your phone charged on the nightstand, the same ones holding your bones together, the same ones making sure that when you breathe in right now, oxygen molecules actually stick to your hemoglobin instead of just bouncing off. It's all one system, one set of instructions running the whole show, and tonight we're going to walk through it, slowly, gently, from the very beginning, and see if we can understand, really understand, how the universe actually works. Let's start with the oldest question. What is stuff made of? You look around any room and you see solid things, walls, furniture, your own hands, and it all feels so permanent, so dense, so undeniably there. But here's the thing, if you could zoom in far enough, past the surface, past the texture, past anything your fingers could feel, you'd find that almost everything you think of as solid matter is empty space. Spectacularly, overwhelmingly empty. If you took a single atom, say a hydrogen atom, the simplest one there is, and you blew it up to the size of a football stadium, the nucleus, the actual solid bit in the center, would be about the size of a marble sitting on the 50-yard line, and the electron, it would be somewhere in the upper bleachers, a tiny speck orbiting that marble, with nothing but empty space in between. That's what you're made of. That's what everything is made of. Marbles and specks, separated by vast nothingness, and yet somehow it all holds together firmly enough that you can pick up a coffee cup without your hand passing through it. Why? How? That's where the story gets good. The ancient Greeks were the first people we know of who really sat down and tried to think this through, without just saying the gods did it and moving on. Around 450 BC, a philosopher named Leucippus and his more famous student Democritus proposed something radical. They said that if you took any piece of matter and kept cutting it in half, over and over, eventually you'd reach a piece so small it couldn't be cut anymore. They called this piece atomos, which literally means uncuttable, and that's where we get the word atom. Now, Democritus didn't have a microscope. He didn't have any instruments at all. He was just thinking, reasoning from first principles, and his idea was that everything in the world, rocks, water, air, flesh, fire, was made of these tiny, indivisible particles, different shapes and sizes of them, hooking together in different combinations to make different substances. It's a stunning piece of intuition when you think about it, because he was essentially right. Not in every detail, obviously, but the core idea that matter is not infinitely divisible, that there's a smallest building block that turned out to be one of the most important ideas in the history of human thought. But here's what's wild. Almost nobody listened to him. Aristotle came along a generation or two later, and Aristotle was arguably the most influential thinker in Western history. And Aristotle thought the atom idea was nonsense. He preferred the idea that all matter was made of 4 elements: earth, water, air, and fire, mixed in different proportions. And because Aristotle's authority was so enormous, his view dominated for nearly 2,000 years. 2,000 years. Democritus's insight just sat there gathering dust, while generation after generation of thinkers tried to explain chemistry and physics using a framework that was fundamentally wrong. It's a good reminder that being right isn't enough. You also have to be right at a time when people are ready to hear it. So let's jump forward. It's the early 1800s now, and a quiet, self-taught English chemist named John Dalton is doing something deceptively simple. He's weighing things. Specifically, he's carefully measuring the masses of chemicals before and after they react with each other. And he's noticing patterns. When hydrogen and oxygen combine to make water, they always combine in the same ratio by weight. Always. Not approximately, not roughly, exactly the same ratio every single time. And this is true for other reactions too. Dalton realizes that the simplest explanation for this is that matter really is made of discrete particles, atoms, and that each type of atom has a specific fixed weight. When atoms combine, they do so in whole number ratios, which is why the weight ratios in chemical reactions are always so clean and consistent. You can't have half an atom of oxygen. It's all or nothing. Dalton published his atomic theory in 1808, and it changed everything. Suddenly, chemistry had a framework that actually made sense. You could predict how much of one substance you'd need to react with another. You could explain why certain compounds existed and others didn't. The atom went from a philosophical curiosity to a working scientific tool. But, and this is important, nobody had actually seen an atom. Nobody had any direct evidence that atoms were real physical objects rather than just a useful bookkeeping trick. And that distinction mattered. For the next 100 years, serious scientists argued about whether atoms were literally real or just a convenient fiction. It sounds strange to us now, but it was a genuine, heated debate. The person who arguably settled it, once and for all, was someone you've definitely heard of, but maybe not in this context. In 1905, a 26-year-old patent clerk in Bern, Switzerland, Albert Einstein, working in his spare time because no university would hire him, published a paper explaining something called Brownian motion. Here's the setup. Back in 1827, a Scottish botanist named Robert Brown had been looking through a microscope at pollen grains suspended in water, and he noticed that the tiny grains jiggled around randomly, constantly, never stopping. Nobody could explain why. Einstein showed mathematically that the jiggling was caused by the pollen grains being bombarded from all sides by water molecules, actual, physical, individual molecules smacking into the pollen like a crowd of invisible people pushing a beach ball around. He didn't just describe this qualitatively. He gave precise mathematical predictions about how far the grains should move over time, predictions that depended on the actual size of the molecules doing the pushing. A few years later, a French physicist named Jean Perrin ran incredibly careful experiments, measured the motion of particles suspended in fluid, and confirmed Einstein's predictions almost exactly. And that was it. Atoms were real, not metaphors, not accounting tricks, real things with real sizes that you could, in principle, count. Now, here's where things start to get really interesting, because the moment scientists accepted that atoms were real, the next question was obvious. What's inside them? Dalton had imagined atoms as tiny, solid, indivisible balls, like miniature billiard balls. But by the late 1800s, there were hints that atoms had some kind of internal structure. The biggest hint came from a British physicist named J.J. Thomson, working at the Cavendish Laboratory in Cambridge. In 1897, Thomson was experimenting with cathode rays, those glowing beams you used to see in old television tubes, and he discovered that these rays were actually streams of tiny particles, much smaller than any atom, and they all carried a negative electrical charge. He called them corpuscles, though we now call them electrons. And the crucial point was this: these electrons were coming out of atoms, which meant atoms weren't indivisible after all. They had parts, smaller things inside them. Thomson proposed a model, sometimes called the plum pudding model, which is a wonderfully British name for a physics theory. He imagined the atom as a blob of positive charge, like the pudding, with tiny negative electrons embedded in it, like raisins or plums scattered throughout. It was a reasonable guess given what he knew, but it was wrong. The person who proved it wrong was one of the most colorful characters in the history of physics. Ernest Rutherford was a New Zealander, big and loud and blunt, the kind of person who filled a room just by walking into it. He'd studied under Thomson at Cambridge, then moved to McGill University in Montreal, and later to the University of Manchester. In 1909, Rutherford and two of his colleagues, Hans Geiger and Ernest Marsden, set up one of the most famous experiments in the history of science. They took a thin sheet of gold foil, incredibly thin, just a few hundred atoms thick, and they fired tiny, fast-moving, positively charged particles at it. These were alpha particles, which we now know are basically helium nuclei, little bundles of protons and neutrons. The idea was simple. Shoot these particles at the gold foil and see where they end up. If Thomson's plum pudding model was right, the positive charge in each atom would be spread out evenly, thinly, like a diffuse cloud. The alpha particles, which were heavy and fast, should punch right through with barely any deflection, like bullets through tissue paper, and most of them did exactly that. But here's the thing that changed everything. A small number of alpha particles, maybe 1 in 8,000, bounced back, not just deflected a little, bounced back toward the source, as if they'd hit something incredibly dense and hard. Rutherford later said it was as if you'd fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. He was genuinely astonished. Think about what that means. Most of the alpha particles sailed straight through, which confirmed that most of the atom really was empty space. But the few that bounced back had to be hitting something tiny, something incredibly dense, something carrying a strong positive charge that could repel the positively charged alpha particles violently enough to send them back the way they came. Rutherford worked out the math, and by 1911 he published his conclusion. All of the atom's positive charge and virtually all of its mass was concentrated in an incredibly small, dense core at the center. He called it the nucleus. And just like that, the picture of the atom changed completely. It wasn't a pudding with raisins. It was more like a tiny solar system, a dense central nucleus with electrons orbiting far away and almost nothing in between. Now, this was thrilling, but it also created a serious problem. And this problem is worth sitting with because it leads us somewhere profound. According to the physics that was understood at the time, what we now call classical physics, the physics of Newton and Maxwell, Rutherford's atom shouldn't be able to exist. Here's why. An electron orbiting a nucleus is a charged particle moving in a circle, and according to Maxwell's equations of electromagnetism, a charged particle that's accelerating and moving in a circle counts as acceleration, even if the speed isn't changing, because the direction should radiate energy in the form of electromagnetic waves constantly, which means the electron should be losing energy continuously, spiraling closer and closer to the nucleus, moving faster and faster, radiating more and more intensely, until it crashes into the nucleus in a tiny fraction of a second. The math said this should happen in about 100 millionth of a second. Every atom in the universe should have collapsed almost instantly, and yet, obviously, they hadn't. You're here. The room around you is here. Something was deeply, fundamentally wrong with the classical picture, and fixing it would require an entirely new way of thinking about reality, a way of thinking so strange, so counterintuitive, that even the people who invented it struggled to believe what their own equations were telling them, and the first real step toward that new understanding came from an unlikely place, not from atoms at all, but from the glow of heated objects, something as simple as a piece of metal glowing red in a furnace. This was the problem of blackbody radiation, and it might sound mundane compared to the drama of atoms and electrons, but it turned out to be the crack in the foundation that brought down the entire classical worldview. So let's talk about what a blackbody actually is, because the name is a little misleading. A blackbody is just an idealized object that absorbs all the radiation that hits it, all wavelengths, perfectly, nothing reflected. And when you heat it up, it glows. Everything glows when it gets hot enough. You've seen this. A stovetop burner turns red. The filament in an old incandescent light bulb glows white hot. The sun glows. Molten lava glows. And here's the thing that physicists noticed in the late 1800s. The color of that glow, the spectrum of light emitted, depends only on the temperature, not on what the object is made of, not on its shape, not on its size. A lump of iron and a lump of carbon, heated to the same temperature, will glow with the same spectrum. That's remarkable when you think about it. It suggests something universal is going on, something fundamental about the relationship between heat and light. And by the 1890s, experimentalists had carefully measured these spectra. They knew exactly what the curve looked like, how much energy was emitted at each wavelength for a given temperature. The curve had a particular shape. It rose steeply, peaked at some wavelength that depended on temperature, and then fell off again at shorter wavelengths. Hotter objects peaked at shorter wavelengths, which is why things go from red to orange to yellow to white to bluish-white as they get hotter. Beautiful, clean, well-measured data. The problem was that nobody could explain it. Two of the best physicists of the era tried, and each got it half right. Lord Rayleigh and James Jeans used classical physics, treating light as a wave and applying the same statistical mechanics that worked so well for gases, and they derived a formula that matched the data beautifully at long wavelengths. Infrared, microwaves, that end of the spectrum. Perfect agreement. But at short wavelengths, at the ultraviolet end, their formula didn't just diverge a little. It went to infinity. It predicted that any heated object should emit an infinite amount of energy at ultraviolet wavelengths. Infinite energy from a warm piece of metal. This was so absurd that it got a dramatic name, the ultraviolet catastrophe, and it wasn't a small error or a missing correction term. It was a fundamental, unambiguous prediction of classical physics that was catastrophically, impossibly wrong. Meanwhile, Wilhelm Wien had derived a different formula that worked at the short wavelength end but failed at long wavelengths. So between Rayleigh, Jeans, and Wien, you had two halves of the answer, and no way to stitch them together using the physics anyone knew. Enter Max Planck. And here's where the story gets wonderfully human, because Planck was not a revolutionary by temperament. Not at all. He was a conservative, meticulous, deeply traditional physicist. Born in 1858 in Kiel, Germany, he came from an academic family. His father was a law professor. His great-grandfather and great-great-grandfather had both been theologians. Planck was the kind of person who believed in order, in the fundamental rationality of nature, in the idea that the laws of physics should be beautiful and consistent and, above all, classical. He didn't want to overthrow anything. He just wanted to solve this one stubborn problem about the black-body spectrum. And in October of 1900, after months of intense work, he found a formula that fit. He essentially interpolate between the Rayleigh-Jeans result and Wien's result, guided partly by mathematical intuition and partly by the experimental data, and he produced an equation that matched the observed spectrum perfectly. Every wavelength, every temperature, perfect agreement. But here's the thing. It was just a formula at first, a mathematical expression that worked. He didn't yet have a physical explanation for why it worked. So he went looking for one. He spent weeks trying to derive his formula from first principles, and he found that the only way to make the math come out right was to assume something that made no physical sense to him whatsoever. He had to assume that energy was not emitted or absorbed continuously, the way classical physics demanded, but in discrete little packets, chunks, specific amounts. He called these chunks quanta, from the Latin word for how much, and the size of each quantum was determined by the frequency of the light. Specifically, the energy of one quantum equaled a constant, which we now call Planck's constant, multiplied by the frequency. E equals h times f. That's it. That's the equation that changed everything. Planck's constant is an incredibly tiny number, about 6.626 times 10 to the negative 34th joule seconds. It's so small that in everyday life, the graininess of energy is completely invisible. It's like saying that water isn't truly continuous, but is made of molecules. Technically true, but when you're filling a bathtub, you'd never notice. The individual quanta of energy are so minuscule that for any normal-sized object, energy looks perfectly smooth and continuous, but at the atomic scale, that graininess matters enormously. Now, Planck himself didn't fully grasp what he'd done. He thought of quantization as a mathematical trick, a computational device that happened to give the right answer. He spent years afterward trying to reconcile it with classical physics, trying to find a way to make the quanta go away. He couldn't. They wouldn't go away, but he never quite accepted that he'd uncovered something truly fundamental about nature. That acceptance would come from someone else, and that someone else was Albert Einstein, again. The same Einstein who in 1905 had explained Brownian motion and proved that atoms were real. In another paper that very same year, 1905, his miracle year, Einstein took Planck's idea and ran with it in a direction that Planck himself would have found alarming. Einstein proposed that light itself was quantized, not just the emission and absorption of light, but light itself, that a beam of light wasn't a continuous wave, the way Maxwell's equations described it, but was actually made up of individual particles of energy, particles we now call photons. Each photon carried an energy equal to Planck's constant times the frequency. High-frequency light, like ultraviolet, came in big energy packets. Low-frequency light, like red or infrared, came in small ones, and Einstein used this idea to explain something called the photoelectric effect, which had been puzzling physicists for years. The photoelectric effect is what happens when you shine light on a metal surface and electrons come flying off. It had been observed since the 1880s, and the weird thing about it was this: whether or not electrons were ejected depended on the color of the light, not its brightness. You could shine a very dim beam of ultraviolet light on a piece of zinc, and electrons would pop off immediately. But you could flood that same piece of zinc with the most intense red light imaginable, blindingly bright red light, and nothing would happen, not a single electron. Classical wave theory couldn't explain this at all. If light were a wave, then brighter light should mean more energy delivered to the surface, and eventually electrons should be knocked loose regardless of color. But that's not what happened. Einstein's explanation was elegant and simple. If light comes in packets, and each packet's energy depends on frequency, then a photon of ultraviolet light carries enough energy to knock an electron free, while a photon of red light doesn't. It doesn't matter how many red photons you throw at the surface. Each individual one is too weak to do the job, and they don't pool their energy together. It's like trying to knock down a door. One person pushing hard enough can do it, but 100 people each pushing with the force of a feather won't, no matter how many of them there are. Each interaction is individual, one photon to one electron, and either the photon has enough energy or it doesn't. This was radical, really radical, because for over a century, the wave nature of light had been considered settled science. Thomas Young's double-slit experiment in 1801 had shown interference patterns that could only be explained by waves. Maxwell's equations described light as electromagnetic waves, and they worked spectacularly well. And now Einstein was saying that light was also particles, not instead of waves, also particles, both at once. This was the beginning of what would become one of the strangest ideas in all of physics: wave-particle duality, the notion that light, and eventually matter too, doesn't fit neatly into either the category of wave or particle, but is something else entirely, something that behaves like one or the other depending on how you look at it. We'll come back to this, because it only gets stranger. But first, let's go back to the atom, because remember, we left the atom in a crisis. Rutherford's solar system model, with electrons orbiting a nucleus, was beautiful but doomed. Classical physics said those orbiting electrons should radiate away their energy and spiral into the nucleus in a fraction of a second. And now we have Planck's idea. Energy comes in quanta, and Einstein's extension. Light itself is quantized. And in 1913, a young Danish physicist named Niels Bohr looked at all of this and had an idea that was, frankly, a little audacious. Bohr was working in Rutherford's lab in Manchester at the time, and he was deeply aware of the atomic stability problem. He was also aware of something else, a beautiful, mysterious pattern in the light emitted by hydrogen atoms. When you take a tube of hydrogen gas and run an electrical current through it, the gas glows, and if you pass that light through a prism, you don't get a continuous rainbow. You get individual, discrete lines of color, specific wavelengths, and nothing in between. Red, blue-green, blue-violet, and a few in the ultraviolet. These spectral lines had been carefully measured by a Swiss school teacher named Johann Balmer back in 1885, and Balmer had discovered that the wavelengths followed a simple mathematical formula, a pattern involving whole numbers, but nobody knew why. It was a pattern without an explanation, a beautiful equation hanging in midair with no physics underneath it, and Bohr realized that quantization could explain it. His proposal was bold and, by the standards of classical physics, completely unjustified. He said, "What if electrons can't orbit the nucleus at just any distance? What if only certain specific orbits are allowed, orbits where the electron's angular momentum is a whole number multiple of Planck's constant divided by 2 pi in these special orbits, and only these orbits? The electron doesn't radiate. It just doesn't." Bohr didn't explain why it doesn't. He simply declared it as a postulate, a rule of the game. And when an electron jumps from a higher orbit to a lower one, it emits a photon whose energy equals the difference in energy between the 2 orbits. And when it absorbs a photon of exactly the right energy, it jumps up. Think about what this means. The atom can only exist in certain energy states, specific, discrete levels, like rungs on a ladder. Not a ramp, a ladder. The electron can be on this rung or that rung, but never in between, and the light emitted by atoms comes in specific colors because each color corresponds to a jump between 2 specific rungs. Balmer's mysterious pattern wasn't mysterious anymore. It was the mathematical fingerprint of these quantum jumps in hydrogen, and when Bohr calculated the predicted wavelengths using his model, they matched the observed spectral lines of hydrogen with stunning precision. This was not a vague, qualitative agreement. The numbers matched to 4 significant figures. for a model built on postulates that violated classical physics in ways that Bohr himself couldn't fully justify. This was extraordinary, but Bohr's model had limitations, and he knew it. It worked beautifully for hydrogen, one proton, one electron, the simplest atom there is, but for anything more complex, for helium with its 2 electrons, for lithium with 3, the model started to struggle. The calculations became intractable, and the predictions didn't match as well. Something deeper was needed. Bohr's model was a brilliant stepping stone, a halfway house between the classical world and whatever came next. But it wasn't the final answer. The final answer would require abandoning even more of our intuitions about how reality works, and it would come from a generation of young physicists in the 1920s who were willing to follow the mathematics wherever it led, no matter how strange the destination. And one of the first clues about just how strange things were going to get came from a French prince, of all people, a doctoral student named Louis de Broglie, who in 1924 asked a question so simple it was almost embarrassing. If light, which everyone thought was a wave, turned out to also be a particle, then could matter, which everyone thought was made of particles, also be a wave? That was de Broglie's question. And it sounds almost too simple, right? Almost like a trick question on a philosophy exam. But de Broglie wasn't being cute. He was being deeply, profoundly serious, and the answer he proposed would crack open the door to the strangest, most powerful theory in the history of science. So let's sit with this for a moment. By 1924, physics was in a genuinely weird place. You had light, this thing that for 2 centuries had been understood as a wave, thanks to Thomas Young's double-slit experiment, thanks to Maxwell's equations, thanks to everything. And now Einstein had shown that it also behaved like a stream of particles, these photons, these little packets of energy, wave and particle, both, depending on how you looked at it. And this wasn't just some abstract theoretical curiosity. The photoelectric effect was real. You could measure it. Light hit a metal surface and knocked out electrons one at a time, in a way that only made sense if light came in discrete chunks, so the duality was real. Even if nobody could fully explain it, de Broglie looked at this situation and thought, well, nature tends to be symmetric. If something we thought was a wave also turns out to be a particle, maybe the symmetry runs the other direction too. Maybe things we think of as particles, electrons, protons, atoms, matter itself, also have a wave nature that we just haven't noticed yet. And he didn't just suggest this as a vague idea. He wrote down a formula. He said that any particle with momentum, and momentum is just mass times velocity, has an associated wavelength. The wavelength equals Planck's constant divided by the particle's momentum. That's it. Lambda equals h/p. one of the most elegant equations in all of physics, and de Broglie proposed it in his doctoral thesis. Think about that. Most doctoral theses are read by maybe 5 people and then sit on a shelf gathering dust. De Broglie's thesis rearranged our understanding of reality. Now, here's why this formula is so clever and why nobody had noticed matter waves before. Planck's constant is tiny, absurdly tiny. It's about 6.6 times 10 to the negative 34 joule seconds. That's a decimal point, followed by 33 zeros, and then a 6. So for anything with everyday mass, a baseball, a grain of sand, the wavelength de Broglie's formula gives you is so incredibly small that it's completely undetectable. A baseball thrown at a pitcher's mound has a de Broglie wavelength that's something like 10 to the negative 34 meters. For reference, an atomic nucleus is about 10 to the negative 15 meters, so the baseball's wavelength is a billion times smaller than an atomic nucleus. You're never going to notice that. It has no practical effect on anything the baseball does. But an electron is tiny. Its mass is about 9 times 10 to the negative 31 kilograms. So when you work out the de Broglie wavelength for an electron moving at typical speeds inside an atom, you get something on the order of nanometers, billionths of a meter, and that's roughly the size of an atom itself, which means the wave nature of the electron isn't some negligible footnote. It's the whole story. The electron's wavelength is comparable to the space it's moving in. Its wave nature dominates its behavior, and here's what's really beautiful about this. Remember Bohr's model? Remember how he just postulated, without any real justification, that electrons could only orbit at certain specific distances from the nucleus? Certain allowed orbits, like rungs on a ladder? Well, de Broglie's idea suddenly gave that rule a physical explanation. If an electron is a wave and it's traveling around the nucleus in a circular orbit, then that wave has to close on itself. It has to form a standing wave, like a vibrating guitar string, except bent into a circle. And a standing wave can only exist if a whole number of wavelengths fit perfectly around the circumference of the orbit. 1 wavelength, 2 wavelengths, 3, but not 1.5, not 2.25, a whole number. And when you work out the math, when you say the circumference of the orbit equals n times the de Broglie wavelength, you get exactly Bohr's quantization condition. Exactly. The mysterious postulate that Bohr had pulled seemingly out of thin air suddenly had a reason. Electrons can only exist in certain orbits because only in those orbits does their wave nature allow them to form stable standing waves. Everywhere else, the wave would interfere with itself destructively and cancel out. It simply couldn't exist there. That's gorgeous. And de Broglie's thesis committee knew it was important, but they weren't entirely sure what to make of it. The story goes that one of the examiners sent a copy to Einstein asking what he thought, and Einstein replied that de Broglie had lifted a corner of a great veil, which is about the highest compliment Einstein ever gave anybody. But the real question was, could you test it? Could you actually show that electrons behave like waves, because a beautiful theory that can't be tested is just philosophy? And the answer came in 1927 from two independent experiments, Clinton Davison and Lester Germer at Bell Labs in the United States, and separately George Paget Thomson, J.J. Thomson's son, which is a wonderful piece of historical symmetry in Scotland. They fired beams of electrons at crystalline materials and observed diffraction patterns. Diffraction is something only waves do. When waves pass through a regular array of obstacles, like atoms arranged in a crystal lattice, they spread out and interfere with each other, creating a distinctive pattern of bright and dark bands. And that's exactly what Davison, Germer, and Thomson saw. Electrons, these things that everyone had been thinking of as tiny billiard balls since J.J. Thomson discovered them 30 years earlier, were diffracting. They were behaving like waves, and the wavelengths they measured matched de Broglie's prediction perfectly. So think about the irony here. J.J. Thomson won the Nobel Prize for showing that the electron is a particle. His son George won the Nobel Prize for showing that the electron is a wave, and they were both right. That's quantum mechanics for you. Now, de Broglie had shown that particles have wave properties, and experiments confirmed it. But his framework was still limited. He could assign a wavelength to a particle, but he couldn't tell you much more than that. What he'd done was point in a direction. Someone else needed to actually build the full theory, and that someone turned out to be an Austrian physicist named Erwin Schrödinger, who in late 1925 and early 1926 did something remarkable. He sat down. Actually, the story is that he went on a holiday to a villa in the Swiss Alps with a woman who was not his wife, and the details of who she was have been lost to history, which is probably for the best. And during this holiday, he derived a wave equation for matter, the Schrödinger equation, and this equation would become the central equation of quantum mechanics, the way Newton's second law is the central equation of classical mechanics. Here's the idea, roughly. If an electron is a wave, then there should be a wave equation that describes how that wave behaves, how it moves, how it changes over time, how it responds to forces. For ordinary waves, like sound waves or water waves, we already had wave equations. Schrödinger needed one for matter waves, and he found it. He wrote down an equation where the thing that's waving, the thing that varies from place to place and moment to moment, is something he called the wave function, usually written with the Greek letter psi, and the equation tells you how psi evolves over time given the forces acting on the particle. When Schrödinger applied his equation to the simplest case, a single electron orbiting a hydrogen nucleus. It worked spectacularly. The equation naturally produced quantized energy levels, not because anyone put them in by hand, the way Bohr had. They emerged automatically from the mathematics, the same way specific notes emerge from a guitar string because of its length and tension. The boundary conditions, the requirement that the wave function be well behaved, that it doesn't blow up to infinity, that it smoothly connects back to itself. Those conditions automatically select only certain solutions, and those solutions correspond to specific energy levels, and those energy levels matched the ones Bohr had found, which matched the observed spectral lines of hydrogen. But Schrödinger's equation could do more. It could handle more complex atoms. It could handle molecules. It was a general framework, not a special case. But here's where things get philosophically thorny, and this is the part that kept physicists arguing for decades, that still keeps some of them arguing today. What is the wave function? What is psi physically? What's actually waving? Schrödinger himself initially thought the wave function represented the electron smeared out in space, that the electron literally was the wave, spread out like a cloud around the nucleus. But that interpretation ran into problems almost immediately. When you actually measure an electron's position, you always find it at a specific point. You never find half an electron here and half an electron there. It's always all or nothing, a definite location. So how can it be a spread-out wave between measurements, but a localized particle when you look? The answer, or at least the answer that most physicists eventually accepted, came from Max Born, a German physicist working in Göttingen. Born proposed in 1926 that the wave function doesn't tell you where the electron is. It tells you the probability of finding the electron in a given place. Specifically, the square of the wave function at any point gives you the probability density, the likelihood per unit volume of detecting the electron there. If you measure where psi squared is large, you're likely to find the electron. Where it's small, you're unlikely to. Where it's zero, you'll never find it there. This was a radical departure from everything physics had been doing for 300 years. Since Newton, physics had been deterministic. You give me the initial conditions, the position and velocity of every particle, and I'll tell you exactly where everything will be at any future time. That was the promise of classical physics. Born's interpretation shattered that promise. Quantum mechanics doesn't tell you what will happen. It tells you the probability of various outcomes. And this isn't because our measurements are imprecise or because we're missing some hidden information. As far as anyone can tell, the randomness is fundamental. It's baked into the fabric of reality itself. Einstein hated this, absolutely hated it. This is where his famous line comes from. God does not play dice with the universe. He could never accept that the deepest level of physical reality was governed by probability rather than certainty, and he spent much of the rest of his life trying to show that quantum mechanics was incomplete, that there had to be some deeper, deterministic theory underneath. But experiment after experiment, decade after decade, has confirmed the probabilistic predictions of quantum mechanics with extraordinary precision. It remains, to this day, the most accurately tested theory in all of science. Some of its predictions have been verified to 11 decimal places. Whatever your philosophical feelings about probability and determinism, the math works. It just works. But we're getting ahead of ourselves a little, because while Schrödinger was up in the Swiss Alps deriving his wave equation, something else was happening in Germany, something that would lead to the exact same physics from a completely different direction, and the person responsible was a 23-year-old wunderkind named Werner Heisenberg, who had a very different philosophy about what physics should even look like. Where Schrödinger was a man of waves, of smooth, continuous functions, of things you could picture in your mind, Heisenberg was almost the opposite. He distrusted pictures. He distrusted the idea that you should even try to visualize what's happening inside an atom. And the story of how he came to his version of quantum mechanics is one of the strangest and most brilliant episodes in the history of science. Heisenberg had been studying under Max Born in Göttingen, and also working closely with Niels Bohr in Copenhagen. He was young, intense, and suffering from terrible hay fever in the spring of 1925. And I mention the hay fever because it's actually part of the story. In June of that year, his allergies got so bad that he asked for 2 weeks off and took a ferry to Helgoland, this tiny wind-swept island in the North Sea, basically a rock sticking out of the water about 50 kilometers off the German coast. Almost no pollen, just sea air and cliffs and not much else. And it was there, on that barren little island, working through the nights, that Heisenberg had his breakthrough. His starting point was a philosophical conviction that might sound strange at first. He believed that physics should only talk about things you can actually observe. You can't see an electron orbiting a nucleus. You've never watched one go around. What you can observe are the frequencies and intensities of the light that atoms emit, the spectral lines. So Heisenberg said, let's build a theory that deals only with those observable quantities. Let's not even try to describe the electron's path or position inside the atom. Let's just find the mathematical relationships between the things we can actually measure. What he ended up with was bizarre. Instead of writing down equations for where a particle is at a given time, he arranged the observable quantities into arrays, grids of numbers, tables where each entry corresponded to a transition between two energy states. And he found that when he multiplied these arrays together, the order mattered. If you had 2 arrays, call them A and B, then A times B was not the same as B times A. Now, with ordinary numbers, multiplication always commutes. 3 times 5 equals 5 times 3, always. But Heisenberg's arrays didn't work that way. He found this deeply unsettling. He actually wrote to a friend saying he wasn't sure his theory made any sense because of this strange property. But when he showed his work to Max Born, Born immediately recognized what Heisenberg had stumbled into. These arrays weren't some new invention. They were matrices, mathematical objects that had been studied for decades. And matrix multiplication is exactly like that. The order matters. A times B does not generally equal B times A. Born realized that what Heisenberg had done, almost by accident, was reformulate quantum mechanics entirely in terms of matrix algebra. And together with Born and another physicist named Pascual Jordan, Heisenberg developed this into a complete framework over the following months. It became known as matrix mechanics, and here's the thing that's genuinely remarkable. Matrix mechanics and Schrödinger's wave mechanics look completely different. One is all about smooth wave functions and differential equations. The other is all about discrete arrays of numbers and matrix algebra. They use different mathematics, different conceptual frameworks, different philosophical starting points. Schrödinger was trying to visualize the atom. Heisenberg was deliberately avoiding visualization, and yet they give exactly the same answers. Every prediction that wave mechanics makes, matrix mechanics makes too. Every energy level, every transition probability, every observable quantity comes out identical. Schrödinger himself proved this equivalence in 1926, showing mathematically that the two formulations were just different ways of expressing the same underlying theory. It's like describing the same landscape in two completely different languages. The words are different, the grammar is different, but they're pointing at the same mountains. Now, this might seem like a technical detail, two equivalent formalisms. Who cares? Pick whichever one you like. But it's actually profound. It tells you something deep about the nature of quantum mechanics. The theory isn't really about waves, and it isn't really about matrices. It's about something more abstract than either of those representations. The mathematics is pointing at a structure that exists independently of how you choose to describe it, and physicists eventually developed a more general framework, thanks largely to Paul Dirac and later John von Neumann, that encompasses both formulations as special cases. In this abstract framework, the state of a quantum system is represented by a vector in what's called a Hilbert space, which is a kind of infinite-dimensional mathematical space. Wave functions and matrix representations are just two different ways of projecting that abstract vector onto something concrete you can calculate with. But let's not get lost in the abstraction. Let's come back to Heisenberg, because he wasn't done. In 1927, he made another contribution that might be even more famous than matrix mechanics, and it's one of those ideas that has seeped so deeply into popular culture that almost everyone has heard of it, even if they're not quite sure what it actually says. I'm talking about the uncertainty principle. Here's what it really says, stripped of all the pop science oversimplification. You cannot simultaneously know both the exact position and the exact momentum of a particle. And this isn't a statement about your measuring equipment being clumsy. It's not that your instruments aren't good enough. It's a fundamental limit built into the structure of reality itself. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and vice versa. There's a specific mathematical relationship. The uncertainty in position multiplied by the uncertainty in momentum is always at least as large as Planck's constant divided by 4 pi. Always. No exceptions. No matter how clever your experiment. Think about what that means. In classical physics, you could, at least in principle, know exactly where something is and exactly how fast it's going. That was the whole foundation of prediction. You measure the initial conditions perfectly, you apply Newton's laws, and you know the future. Heisenberg's uncertainty principle says that perfect initial conditions are impossible. Not practically impossible, theoretically impossible. The universe simply does not have a state where a particle has both a definite position and a definite momentum at the same time. And here's where it connects back to what we were talking about with de Broglie's matter waves. Remember how every particle has an associated wavelength? Well, a wave that has a perfectly defined wavelength, a pure sine wave stretching on forever, is spread out over all of space. It doesn't have a position. And a wave that's perfectly localized, concentrated at a single point, is a spike, and a spike doesn't have a well-defined wavelength. You can make something in between, a wave packet that's somewhat localized and has a somewhat defined wavelength. But you always trade off between the two. The uncertainty principle is really just a mathematical consequence of the wave nature of matter. It falls right out of the formalism. Now, there's a common misconception that the uncertainty principle is about the act of measurement disturbing the system, like you shine light on an electron to see where it is, and the photon kicks the electron, changing its momentum. Heisenberg himself actually used an argument like this in his original paper, the famous gamma-ray microscope thought experiment. And while that kind of measurement disturbance is real, it's not the deepest reason for the uncertainty principle. The deeper reason is that quantum states simply don't have simultaneous sharp values for both position and momentum. It's not that the measurement messes things up. As far as quantum mechanics is concerned, those precise simultaneous values don't exist. This was the heart of the argument between Einstein and Bohr that would play out over years. Einstein kept trying to devise thought experiments that would beat the uncertainty principle. Clever setups where you could, in principle, measure both position and momentum precisely. And every single time, Bohr found the flaw in the argument. Every single time, When you carefully accounted for all the physics the uncertainty principle held, their debates at the Solvay conferences in 1927 and 1930 are legendary in the history of physics. Two of the greatest minds ever, going back and forth, each pushing the other to sharpen their thinking. And you know what's beautiful about this? The argument made the theory stronger. Einstein's challenges forced Bohr and others to think more carefully about what quantum mechanics actually means, about the nature of measurement, about the relationship between the mathematical formalism and physical reality. These aren't just technical questions. They touch on philosophy, on what it means to know something, on what reality is when no one is looking. But let's step back for a moment and take stock of where we are. Because by 1927, quantum mechanics was essentially complete as a mathematical framework. You had Schrödinger's wave equation. You had Heisenberg's matrix mechanics. You had Born's probabilistic interpretation. You had the uncertainty principle. You had Dirac beginning to unify everything into an elegant, abstract framework. And all of it worked. It predicted the behavior of atoms, the spectra of elements, the outcomes of experiments, with stunning accuracy. But there was a problem. Everything so far was non-relativistic. Schrödinger's equation works beautifully for electrons moving at everyday speeds, but it doesn't account for Einstein's special relativity, and electrons in heavy atoms, where the nuclear charge is large, move at a significant fraction of the speed of light. So you need a version of quantum mechanics that's compatible with relativity. And this is where Paul Dirac enters the story in the most spectacular way. Dirac was, and I don't think this is an exaggeration, one of the most remarkable physicists who ever lived. He was extraordinarily quiet, almost pathologically laconic. There are dozens of stories about his silence. Colleagues would ask him a question, and he'd simply say yes or no, and nothing else. Niels Bohr once joked that Dirac was the strangest man who had ever visited his institute. But when Dirac wrote physics, it was like poetry. His equations had an aesthetic clarity that other physicists found almost eerie. In 1928, Dirac set out to find a quantum equation for the electron that was consistent with special relativity. Schrödinger had actually tried this first, before deriving his famous non-relativistic equation. He'd attempted a relativistic version, but it gave wrong predictions for hydrogen. The equation Schrödinger abandoned was later developed by Oscar Klein and Walter Gordon, and is now called the Klein-Gordon equation. It works for certain particles, but not for electrons, and the reason turns out to be deep. Electrons have a property called spin, and the Klein-Gordon equation doesn't account for it. So Dirac took a different approach. He wanted an equation that was first order in time, meaning it involved only the first derivative with respect to time, just like Schrödinger's equation, but also first order in space, to treat space and time on equal footing as relativity demands. And when he worked through the mathematics, he found that this was only possible if the wave function had 4 components instead of 1, and if the equation involved a new kind of mathematical object, 4 by 4 matrices, now called the Dirac gamma matrices. The equation he wrote down was elegant and compact, and when he solved it for the hydrogen atom, something magical happened. Electron spin, that mysterious property that had been bolted onto quantum mechanics by hand as an extra assumption by Wolfgang Pauli in 1924, fell out of Dirac's equation automatically, didn't put spin in. It emerged, all on its own, as a natural consequence of combining quantum mechanics with special relativity. Think about that for a second. A property of the electron that had seemed arbitrary, that had to be postulated as an additional quantum number, turned out to be required by the marriage of 2 deeper theories. That's the kind of moment that makes physicists believe they're uncovering something real about the universe, not just building clever models. But Dirac's equation had another surprise in store, and this one was even more startling. When he solved the equation, he found that it had solutions with negative energy. Now, in classical physics, you just throw those away. Negative energy states don't make physical sense, so you ignore them. But in quantum mechanics, you can't do that so easily, because quantum mechanics is a theory about transitions. An electron in a high energy state can emit a photon and drop to a lower energy state. That's how atoms radiate light. We talked about that with Bohr's model, right? The electron jumps down, and the energy difference leaves as a photon. Well, if negative energy states exist, then what stops an ordinary electron from radiating away its energy and tumbling down into one of those negative energy solutions, and then tumbling further and further, releasing infinite energy as it cascades into ever more negative states? Nothing, apparently, which would mean that all matter is fundamentally unstable. Every electron in every atom in your body would want to plummet into this bottomless pit of negative energy. Obviously, that doesn't happen, so Dirac had a problem, and here's where his thinking got genuinely audacious. In 1930, Dirac proposed something that sounds almost absurd at first. He said, "What if all those negative energy states are already filled, every single one of them occupied by an electron, forming an infinite sea of negative energy electrons that stretches across all of space?" You don't notice this sea for the same reason you don't notice the air pressure on your skin most of the time. It's uniform, it's everywhere, and it's the background against which everything else happens. If every negative energy state is already occupied, then the Pauli exclusion principle, which says no 2 electrons can share the same quantum state, prevents any ordinary positive energy electron from falling down into those states. They're all taken, problem solved, at least in a sense. But Dirac realized this picture had a wild consequence. If you pumped enough energy into the vacuum, into this sea, you could knock one of those negative energy electrons up into a positive energy state. You'd create a normal electron, sure, but you'd also leave behind a hole in the sea. And that hole, that absence of a negative energy, negatively charged electron, would behave exactly like a particle with positive energy and positive charge. It would look, to any experiment, like a positively charged electron. Dirac initially wondered if this could be the proton. The proton is positively charged after all. But the math didn't work. The hole had to have the same mass as the electron, and the proton is nearly 2,000 times heavier. So Dirac, somewhat reluctantly, predicted the existence of a completely new particle, a positively charged electron, an anti-electron. He published this in 1931, and a lot of physicists thought it was, frankly, a bit much. A whole new particle conjured out of mathematical formalism, an infinite invisible sea of electrons pervading all of space. It felt like science fiction. And then, in 1932, Carl Anderson at Caltech was studying cosmic rays using a cloud chamber, a device where charged particles leave visible trails of condensation as they pass through supersaturated vapor. Anderson had placed a lead plate across the middle of his chamber, and a strong magnetic field curved the paths of charged particles. He kept seeing tracks that curved the wrong way. They curved like electrons, with the same gentle radius that indicated a light particle, but in the opposite direction, meaning they carried positive charge. He called them positrons. And just like that, Dirac's seemingly outlandish prediction was confirmed. Antimatter was real. Let that sink in for a moment. A 25-year-old theorist, working purely with equations, trying to make quantum mechanics consistent with special relativity, predicted the existence of a form of matter that no one had ever seen, that no one had even imagined, and it was found in a laboratory within 2 years. This is one of the most stunning predictive successes in the history of science. Not engineering in the traditional sense, maybe, but engineering of ideas, building a theoretical structure so carefully that it tells you something about reality that you didn't put in. Now, the Dirac Sea picture, that infinite ocean of filled negative energy states. It works in the sense that it gives you the right predictions, but it's conceptually awkward. An infinite number of invisible electrons filling all of space is a lot of ontological baggage. And as quantum field theory developed through the 1930s and 1940s, physicists found a cleaner way to think about all of this. Instead of talking about holes in a sea, they learned to talk about particles and antiparticles on equal footing as excitations of underlying quantum fields. But we're getting ahead of ourselves. The key point, the thing to carry with you as you settle deeper into whatever comfortable position you've found, is that Dirac's equation didn't just describe the electron, it revealed that every particle in the universe has a mirror partner, an antiparticle, with the same mass but opposite charge, and that revelation came not from experiment, not from observation, but from the internal logic of the mathematics itself. So by the early 1930s, the landscape of physics had transformed almost beyond recognition. In barely a decade, scientists had gone from Bohr's simple planetary model to a full quantum mechanical framework, extended it to include special relativity, and discovered antimatter. But there was still an enormous piece missing. Quantum mechanics could describe electrons, and it could describe photons, the particles of light, but it didn't yet have a coherent way of describing how electrons and photons interact with each other. And that interaction, the exchange of electromagnetic force between charged particles, is responsible for essentially all of chemistry, all of material science, all of biology. It's the force that holds your atoms together, that makes molecules bond, that lets proteins fold, that lets your neurons fire. If you want to understand how the universe actually works at the deepest level, you need a theory of this interaction. The theory that eventually emerged is called quantum electrodynamics, QED for short, and its development is one of the great intellectual dramas of the 20th century. It took nearly 20 years to get right. It almost broke the careers of several brilliant people. And when it was finally completed, it became the most precisely tested theory in all of science. Not approximately correct, not pretty good, the most accurate. But the road there was brutal. Here's the thing. When physicists in the 1930s tried to calculate how an electron interacts with the electromagnetic field using the tools they had, Dirac's equation, the newly developing quantum field theory, they kept getting infinity, not large numbers. Infinity. You'd set up a perfectly reasonable calculation, like asking what the self-energy of an electron is. How much energy is contained in the electron's own electromagnetic field? And the answer would come out as infinity. Or you'd try to calculate the probability that two electrons scatter off each other by exchanging photons, and the first approximation would give you a sensible answer. But the next level of approximation, the correction terms, would blow up to infinity. This was deeply disturbing. It wasn't a minor technical issue. It seemed to suggest that the whole framework of quantum field theory was fundamentally broken. Through the 1930s and into the early 1940s, many of the best minds in physics struggled with this problem and got nowhere. Some people, including Dirac himself, believed that entirely new physics was needed, that the whole approach was a dead end. And then the war came. World War II pulled physicists out of their universities and into military research. Many of the people who would eventually solve the infinity problem spent the war years working on radar, or on the Manhattan Project, or on other classified programs. Physics didn't stop during the war, but fundamental theoretical physics largely paused. People were busy building things, deadly things, world-changing things, and the deep puzzles of quantum field theory sat on the shelf, waiting. When the war ended, something remarkable happened. The experimentalists came back to their labs with dramatically improved technology that had been developed for military purposes, but could now be turned to fundamental science. Microwave techniques perfected for radar, for instance, could be used to probe the structure of atoms with unprecedented precision. And in 1947, Willis Lamb at Columbia University used exactly these techniques to measure something extraordinary. He was looking at two energy levels in the hydrogen atom that, according to Dirac's equation, should have been exactly the same. Two specific quantum states, the two S1/2 and two P1/2 states, if you want the technical labels, that Dirac's theory predicted should have identical energies, but Lamb found they didn't. There was a tiny difference, a tiny shift, amounting to about 1,000 megahertz. This became known as the Lamb shift, and it was announced at a famous conference at Shelter Island, New York, in June of 1947. Now, 1,000 megahertz might not sound tiny, but in terms of energy, relative to the overall energy levels of hydrogen, it's a minuscule correction. But it was real, it was measurable, and Dirac's equation couldn't explain it. The shift had to be coming from somewhere, and the most natural explanation was that it came from exactly those quantum field theory corrections that kept giving infinity, the interaction of the electron with the electromagnetic field's own quantum fluctuations, the constant buzzing of virtual photons being emitted and reabsorbed. So the challenge was clear. Could you somehow extract a finite, meaningful answer from those infinite calculations? Could you tame the infinities? Among the people sitting in the audience at Shelter Island was a young physicist from Cornell named Richard Feynman. He was 30 years old. He'd spent the war at Los Alamos working on the bomb, and he'd been quietly developing his own deeply original way of thinking about quantum mechanics, a formulation based on something called the path integral, where instead of tracking a particle's wave function, you sum over every possible path the particle could take between 2 points, weighting each path by a phase factor related to the classical action. It sounds crazy, summing over infinitely many paths, but it worked. It gave the same answers as Schrödinger's equation, as Heisenberg's matrices, as Dirac's formalism. But it did so from a completely different starting point. A starting point that was, in Feynman's hands, almost visual, almost cinematic, and that mattered enormously. Because when you're trying to deal with quantum electrodynamics, when you're trying to calculate what happens when electrons interact with photons and virtual particles pop in and out of existence, having the right mental picture, the right bookkeeping system, can make the difference between drowning in infinities and actually getting an answer. So let's talk about what Feynman did, because it's one of the great intellectual achievements of the 20th century, and it happened remarkably fast. Within about 2 years of that Shelter Island conference, 3 physicists, working mostly independently, cracked the problem of taming those infinities. Richard Feynman at Cornell, Julian Schwinger at Harvard, and Shinichiro Tominaga in Tokyo. Each of them found a way to extract finite, physically meaningful predictions from quantum electrodynamics, and their approaches looked wildly different on the surface. Schwinger's method was mathematically dense, formal, almost baroque in its elegance, pages and pages of careful algebra. Tominaga had developed a similar formalism in Japan during the war, largely cut off from Western physics, which is remarkable when you think about it. And then there was Feynman, who drew pictures. He did much more than draw pictures. But the pictures are what everyone remembers, and for good reason. Feynman diagrams, those little sketches with lines and squiggly lines and vertices, became one of the most powerful tools in all of theoretical physics. Here's how they work, roughly. You want to calculate the probability that two electrons scatter off each other, say. In Feynman's approach, you draw every possible way that interaction could happen. The simplest way. One electron emits a virtual photon, the other electron absorbs it, and they both change direction. That's one diagram. Two straight lines for the electrons, one wavy line for the photon connecting them. And that diagram corresponds to a specific mathematical expression, an integral you can actually compute, and the answer you get from that one diagram is pretty good. It gives you the classical electromagnetic force between the electrons, basically Coulomb's law translated into quantum language. But that's only the first approximation. There are more complicated diagrams. What if the virtual photon, on its way from one electron to the other, briefly splits into an electron-positron pair, which then annihilates back into a photon? That can happen. Quantum mechanics says anything that isn't forbidden will happen, at least some of the time. So you draw that diagram too. It's got a little loop in the middle of the photon line, and that diagram also corresponds to a mathematical expression you can write down. And there are even more complicated diagrams, loops within loops, photons emitting and reabsorbing other photons, electrons briefly splitting into an electron and a photon and recombining. Each diagram is more complex. Each one contributes a smaller correction, and in principle, you need to sum all of them, infinitely many diagrams, to get the exact answer. Now here's where the infinities come back in. Some of those diagrams, with loops, when you actually compute the integrals, give you infinity. The loop integral diverges, and this was the old problem, the problem that had plagued quantum field theory since the 1930s. But here's what Feynman, Schwinger, and Tominaga each realized in their own way. The infinities aren't random. They have a very specific structure. They always show up in the same places, in corrections to the electron's mass, in corrections to the electron's charge, in corrections to the way the photon propagates. And the key insight, the breakthrough, was this. Those infinite corrections can be absorbed into a redefinition of the physical quantities themselves. Let me try to make that concrete, because it's subtle and it's beautiful. Think about the electron's mass. In the equations, you start with some bare mass, the mass the electron would have if it didn't interact with the electromagnetic field at all. But of course it does interact. It's constantly emitting and reabsorbing virtual photons, surrounded by this cloud of quantum fluctuations, and those fluctuations contribute to its effective mass. They make the electron behave as if it's slightly heavier. When you calculate that contribution, you get infinity, which seems catastrophic. But here's the thing, you never actually measure the bare mass. You can't. Every experiment you ever do measures the electron with its cloud of virtual photons already included. The mass you measure in the lab, 9.109 times 10 to the minus 31 kilograms. That's the physical mass, the bare mass plus all the infinite corrections bundled together. So what if you just say, fine, I don't know the bare mass, I'll never know the bare mass, but I know the physical mass because I measured it. Let me take that measured value and use it in my calculations, and let the bare mass be whatever it needs to be, even if it's formally infinite, so that the physical mass comes out right. This procedure is called renormalization, and it sounds like a trick. It sounds like you're just sweeping infinity under the rug. And honestly, a lot of physicists felt that way at first. Dirac himself never liked it. He thought it was mathematically ugly, a sign that something deeper was wrong. But here's why it works, and why it's more than a trick. Once you absorb the infinities into a finite number of measurable quantities, the electron's mass, the electron's charge, and the normalization of the fields, every other prediction of the theory comes out finite. Every single one. You feed in a handful of measured numbers, and out comes an infinite number of predictions, all finite, all testable, and not just finite, spectacularly, almost unbelievably accurate. The Lamb shift, that tiny energy splitting that started this whole crisis, when you calculate it using renormalized quantum electrodynamics, when you add up the contributions from the relevant Feynman diagrams, the virtual photon loops, the electron self-energy corrections, the vertex corrections, you get a number, and that number matches Lamb's measurement, not approximately, not roughly. It matches to extraordinary precision. As techniques improved over the following decades, the agreement between QED predictions and experimental measurements became one of the most precise in all of science. The most famous example is the anomalous magnetic moment of the electron, a quantity called G-2. The electron behaves like a tiny magnet, and the strength of that magnet is characterized by a number called G. Dirac's equation predicts G equals exactly 2, but quantum corrections, those loop diagrams, shift it slightly. The current theoretical prediction, calculated from QED diagrams up to 10th order, involving more than 12,000 diagrams, agrees with the experimental measurement to about 1 part in a trillion. 1 part in a trillion. That's like measuring the distance from New York to Los Angeles and getting it right to within the width of a human hair. It's the most precisely tested prediction in the history of science. So by the early 1950s, quantum electrodynamics was solved. Feynman, Schwinger, and Tominaga shared the Nobel Prize in 1965 for this work. Freeman Dyson, a young British mathematician who had come to the United States, showed in 1949 that Feynman's and Schwinger's approaches were mathematically equivalent, different languages for the same physics, and Feynman's diagrams became the standard tool, not because they were more rigorous than Schwinger's methods, but because they were more intuitive, more practical, more portable. You could teach a graduate student to draw Feynman diagrams and start computing. Schwinger's approach required a kind of virtuoso mathematical skill that few possessed. Feynman democratized the calculation, but QED, triumphant as it was, only described one force, electromagnetism. And by the 1950s, physicists knew there were other forces that needed quantum treatment. There was gravity, of course, but gravity was so weak at the subatomic level that you could ignore it for particle physics purposes. The two forces that demanded attention were the strong force, which held atomic nuclei together, the force that bound protons and neutrons despite the protons' mutual electrical repulsion, and the weak force, which was responsible for certain kinds of radioactive decay, like beta decay, where a neutron transforms into a proton while emitting an electron and a neutrino. And here's where the story gets really interesting, because physicists didn't just want to describe these forces, they wanted to unify them. They wanted to find a deeper framework, a pattern, a symmetry that connected seemingly different forces the way Maxwell had connected electricity and magnetism a century earlier. And the tool they used to do this was something called gauge symmetry, a mathematical structure that, once you understand it, turns out to be breathtakingly powerful. It's the idea that the laws of physics don't change when you perform certain transformations on the fields, and that requiring this invariance actually forces the existence of the force-carrying particles themselves. In QED, the gauge symmetry is relatively simple. It's based on a mathematical group called U1, and the requirement that the electron field respect this symmetry is precisely what demands the existence of the photon. The photon isn't just there because we observe it. In a deep sense, it has to be there, because without it, the symmetry breaks and the equations become inconsistent. So the question became, what if the strong force and the weak force have their own gauge symmetries, their own mathematical groups, their own force-carrying particles that exist because the symmetry demands them? This line of thinking, pursued through the 1950s and 1960s by physicists like Chen-Ning Yang, Robert Mills, Sheldon Glashow, Abdus Salam, Steven Weinberg, and many others eventually led to what we now call the Standard Model of particle physics. And the story of how it came together is full of wrong turns, brilliant guesses, and at least one idea that seemed completely useless for about a decade before turning out to be absolutely essential to the whole thing. That idea was the Higgs mechanism. And to understand why it mattered so much, you first have to understand the problem it solved. A problem that, for years, seemed like it might kill the entire gauge symmetry program before it even got started. Here's the issue. When Yang and Mills first wrote down their generalization of gauge symmetry in 1954, extending the U1 symmetry of electromagnetism to more complex mathematical groups like SU2, the equations were beautiful. They were elegant. They had a gorgeous internal logic. But they made a prediction that was obviously catastrophically wrong. The equation said that the force-carrying particles, the analogues of the photon for these new forces, had to be massless, just like the photon itself, zero mass, traveling at the speed of light with an infinite range. And that was fine for electromagnetism, because the photon is massless, and electromagnetism does have infinite range. But the weak force? The weak force has an incredibly short range. It only operates over distances smaller than an atomic nucleus, and a force with a short range requires heavy force carriers. That's a deep connection. The heavier the particle mediating a force, the shorter the distance over which that force can reach. It's almost like the particle is too heavy to travel far before it winks out of existence, handed back to the quantum vacuum. So Yang-Mills' theory predicted massless force carriers. But the weak force needed massive ones, and you couldn't just add mass by hand. You couldn't just write in a mass term into the equations, because doing so would destroy the very gauge symmetry that made the theory work in the first place. The symmetry and the mass seemed fundamentally incompatible. It was like being told you could have a beautiful house, but only if it had no roof. The architecture demanded openness, but physics demanded shelter. And for about a decade, nobody could figure out how to square that circle. This is where a handful of theorists came in, working somewhat independently. In 1964, Peter Higgs in Edinburgh, François Englert and Robert Brout in Brussels, Gerald Guralnick, Carl Hagen, and Tom Kibble in London, they all hit on essentially the same insight, though they approached it from slightly different angles, and the insight was this. What if the symmetry is there in the fundamental laws, but it's hidden? What if the equations respect the gauge symmetry perfectly, but the actual state of the universe, the vacuum, the ground state, the lowest energy configuration of everything, doesn't? The technical term is spontaneous, symmetry breaking. And it's one of those ideas that sounds abstract until you see a good analogy, and then it suddenly clicks. Think about a pencil balanced perfectly on its tip. The setup is symmetric. The pencil could fall in any direction, and the laws of physics don't prefer one direction over another. Perfect rotational symmetry, but the pencil doesn't stay balanced. It falls, and once it falls, it picks a direction. The symmetry of the underlying law is still there. Gravity doesn't care which way the pencil falls, but the actual outcome, the state you observe, has broken that symmetry. One direction has been chosen, even though the choice was arbitrary. Now imagine something like that happening to the entire universe. Imagine a field, not an electromagnetic field, not a gravitational field, but a new kind of field that permeates all of space. And imagine that this field, like the pencil, has a symmetric configuration that's unstable. The lowest energy state isn't the symmetric one. Instead, the field settles into a lopsided configuration, picking a particular value everywhere in space. The underlying equations still have the full gauge symmetry, but the vacuum state, the canvas on which everything else happens, doesn't. And here's what's really clever. When the force-carrying particles interact with this field in its lopsided state, they behave as if they have mass. The symmetry is technically still there, hiding in the mathematics, but its observable consequences have changed completely. The force carriers are now massive. The force now has a short range, and you didn't have to break the symmetry by hand. It broke itself, spontaneously, like the pencil falling over. This is the Higgs mechanism, and the field that does this, the Higgs field, would have its own particle, a quantum of its own vibrations, which we now call the Higgs boson. When Higgs first proposed this in 1964, the paper was actually rejected by the journal Physics Letters. They didn't think it was important enough. He revised it, added a crucial paragraph pointing out that the theory predicted a new massive particle, and sent it to Physical Review Letters instead, where it was published. But even after publication, the idea sat there for a while. It was a solution looking for a problem to attach to. The mechanism existed in the abstract, but nobody had yet built a complete, realistic theory of the weak force that used it. That's where Weinberg and Salam come back into the story. In 1967, Steven Weinberg was working at MIT, trying to apply the Higgs mechanism to the strong force and getting nowhere. And then, and this is one of those wonderful moments in physics where the breakthrough comes from realizing you've been looking at the wrong problem. He realized the mechanism fit the weak force perfectly. He took Glashow's earlier work from 1961, which had proposed a gauge theory unifying the electromagnetic and weak forces based on the symmetry group SU2XU1, and he combined it with the Higgs mechanism to give mass to the weak force carriers while leaving the photon massless. The result was a unified electroweak theory, one framework, one set of equations, describing both electromagnetism and the weak nuclear force as different aspects of a single underlying gauge symmetry that had been spontaneously broken by the Higgs field. Salam arrived at essentially the same theory independently, working in Trieste, and the theory made specific predictions. It said there should be 3 massive force carriers for the weak force, 2 charged ones, called the W plus and W minus, and 1 neutral one, called the Z. It predicted their approximate masses. It predicted specific relationships between different weak-forced processes, and for a few years, almost nobody paid attention. The paper Weinberg published in 1967 received almost no citations for the first few years, partly because the theory hadn't yet been proven to be mathematically consistent. Specifically, nobody had shown that it was renormalizable, that the infinities could be tamed the way they'd been tamed in QED. That proof came in 1971 from a young Dutch graduate student named Gerard Hooft, working with his advisor Martinus Veltman at Utrecht, and this was a thunderbolt. Hooft showed that Yang-Mills theories with spontaneous symmetry breaking were renormalizable. You could calculate with them. You could extract finite, meaningful predictions. Suddenly, the Weinberg-Salam model wasn't just an elegant idea. It was a real, calculable theory, and the citations to Weinberg's 1967 paper exploded almost overnight. The physics community pivoted. This was the path forward. The experimental confirmation came in stages. In 1973, the Gargamel bubble chamber at CERN detected neutral current interactions, processes mediated by the Z boson, exactly as the theory predicted. And then, in 1983, the W and Z bosons themselves were directly produced and observed at CERN's superproton synchrotron, in experiments led by Carlo Rubbia and Simon van der Meer. The masses matched the predictions beautifully. The W bosons came in at about 80 GeV, the Z at about 91 GeV, roughly 80 and 90 times the mass of a proton. These are heavy particles, and their heaviness is precisely why the weak force is so short-ranged, why it only operates inside atomic nuclei, why it took so long to understand. So now you had electromagnetism and the weak force unified. But what about the strong force? The force that holds quarks together inside protons and neutrons, the force that ultimately holds the atomic nucleus together. That story was developing in parallel, and it has its own cast of characters and its own surprises. The strong force turned out to be described by a gauge theory based on the symmetry group SU3, and the theory is called quantum chromodynamics, or QCD. The chromo refers to color, not actual color, of course, but a whimsical label for a new kind of charge that quarks carry. Just as electric charge comes in positive and negative, color charge comes in 3 types, traditionally called red, green, and blue. And just as the electromagnetic force is mediated by photons, the strong force is mediated by particles called gluons, 8 of them, in fact, corresponding to the 8 generators of the SU3 symmetry group. But here's what makes the strong force so strange, so different from electromagnetism. Gluons themselves carry color charge. Photons don't carry electric charge. They're electrically neutral, which is why they don't interact with each other. But gluons carry the very charge they mediate. They interact with each other, and this self-interaction changes everything about how the force behaves. At very short distances inside a proton, quarks feel a relatively weak, strong force. They're almost free, bouncing around like billiard balls in a very small box. This is called asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Politzer in 1973. And it was a shock because everyone expected forces to get stronger at shorter distances, not weaker. But at larger distances, if you try to pull two quarks apart, the force doesn't diminish. It stays constant or even grows. The gluon field between them forms something like a tube, a string of energy, and as you stretch it, you're pumping more and more energy into it until eventually there's enough energy to create a new quark-antiquark pair out of the vacuum. You never get an isolated quark. They're permanently confined. This is why you've never seen a free quark, why nobody has. Confinement is one of the most remarkable phenomena in all of physics. And while we have overwhelming numerical evidence that QCD produces it, from massive supercomputer simulations of the theory, a rigorous mathematical proof of confinement remains one of the great open problems. There's literally $1 million prize waiting for whoever proves it. So by the mid-1970s, the pieces had come together. Electromagnetism, the weak force, and the strong force, all described by gauge theories. U1 for electromagnetism, SU2, SU1 for the electroweak theory, spontaneously broken by the Higgs field, SU3 for QCD. Together, the full symmetry group is SU3, SU2, SU1, and the theory built on this foundation is the standard model of particle physics. It includes 6 quarks, 6 leptons, the electron and its heavier cousins, the muon and tau, plus 3 neutrinos, the photon, the W and Z bosons, 8 gluons, and the Higgs boson. That's it. That's the complete inventory of fundamental particles as far as we know, and every experiment ever conducted at every particle accelerator ever built has been consistent with this model, and the precision is staggering. Remember the electron's anomalous magnetic moment from QED, accurate to 1 part in a trillion? The standard model extends that kind of precision across a vast range of phenomena, the masses of the W and Z bosons, the rates of hundreds of different particle reactions, the detailed properties of the Higgs boson discovered at CERN's Large Hadron Collider in 2012. All of it matches. The Higgs discovery, by the way, was the last missing piece. Nearly half a century after Higgs wrote that paragraph about a new massive particle, after his paper was rejected and then accepted and then mostly ignored. The particle was found at a mass of about 125 GeV, behaving exactly as the theory predicted. But here's the thing. For all its astonishing success, the Standard Model is clearly not the final answer. And physicists know this because of gravity. Gravity is the one force that the Standard Model doesn't include, and it's not for lack of trying. The problem is deep, structural, and it touches on questions that connect the very large to the very small in ways that nobody has fully figured out yet. And that's where we are right now, at the edge of what we know, staring at a gap in the picture that's been open for nearly a century. So let's talk about it. Let's talk about gravity and why it's so different, and what it might be telling us about the universe at the deepest level we can imagine. The other three forces, electromagnetism, the weak force, the strong force, they all fit beautifully into the quantum framework. You write down a gauge symmetry, you get force-carrying bosons, you quantize the fields, and you can calculate. Gravity on the surface seems like it should work the same way. Einstein's general relativity describes gravity as the curvature of space-time, and you can try to quantize it the same way you'd quantize any other field theory. You'd say, okay, the gravitational field has ripples, and those ripples should come in discrete quanta, and we'll call those quanta gravitons, massless, spin-2 particles that mediate the gravitational force, just like photons mediate electromagnetism. And at low energies, this actually works fine. You can do calculations with gravitons, and they give sensible answers. The problem shows up when you push to higher energies, shorter distances, more extreme conditions. When you try to calculate quantum gravitational effects at very small scales, we're talking about the Planck scale, around 10 to the minus 35 meters, a distance so absurdly tiny that it makes a proton look like a galaxy. The math explodes. You get infinities, just like the infinities that plagued QED back in the 1940s. But here's the crucial difference. When Feynman and Schwinger and Tominaga found infinities in QED, they could absorb them through renormalization. They could tuck those infinities into a finite number of measurable quantities and get on with making predictions. With gravity, you can't. The infinities multiply. At every order of calculation, new types of infinities appear that require new parameters to absorb them, and you end up needing an infinite number of parameters, which means you can't predict anything at all. The theory is, in the technical language, non-renormalizable. It's not that the calculations are hard, it's that the framework itself breaks down. Gravity, treated as a quantum field theory in the usual way, simply does not work. Now, you might think, well, maybe that's fine. Maybe gravity is just classical. Maybe it doesn't need to be quantized. And for most practical purposes, that's exactly how physicists treat it. General relativity handles the large-scale structure of the universe, galaxies, black holes, the expansion of space, and quantum mechanics handles the small stuff, and they almost never need to talk to each other. The gravitational force between two electrons is something like 40 orders of magnitude weaker than the electromagnetic force between them. 40 orders of magnitude, that's a 1 followed by 40 zeros. So in any particle physics experiment you could ever build, gravity is utterly negligible. You can just ignore it, but there are situations, extreme situations, where you can't ignore it. And those situations are exactly the ones where the deepest questions live. Think about the center of a black hole. General relativity says that a collapsing star can form a singularity, a point of infinite density where space-time curvature becomes infinite. But infinite is physics speak for our theory just broke. The theory is screaming at us that something else is happening, something that requires understanding gravity at quantum scales. Or think about the very beginning of the universe. Run the expansion of the cosmos backward, and you reach a moment, the Big Bang, where all the matter and energy in the observable universe was compressed into a region smaller than an atom, a region where both quantum effects and gravitational effects were enormous simultaneously. To understand that moment, you need a theory that combines both. You need quantum gravity, and we don't have it. It's not for lack of brilliant people trying. This is arguably the biggest open problem in fundamental physics, and it's been attacked from multiple directions for decades. Let me tell you about the two most prominent attempts, because they're fascinating, and they reveal very different philosophies about what the answer might look like. The first is string theory. The basic idea emerged in the late 1960s, and it's beautifully simple to state, even if the details are staggeringly complex. Instead of treating fundamental particles as point-like objects, zero-dimensional dots, string theory proposes that they're actually tiny, one-dimensional vibrating strings, unimaginably tiny, down at the Planck scale. And just like a guitar string can vibrate in different modes to produce different musical notes, these fundamental strings can vibrate in different patterns, and each pattern corresponds to a different particle. One vibration mode gives you a photon, another gives you an electron, another gives you a quark. And here's the thing that got people really excited. One of the vibration modes automatically, unavoidably, gives you a massless spin-2 particle, a graviton. Gravity isn't something you have to bolt onto string theory. It emerges naturally from the mathematics. The theory insists on it. This was discovered in the early 1970s by John Schwarz and Joel Scherk, and at first almost nobody cared. String theory had originally been proposed as a theory of the strong force, and when QCD came along and did that job better, strings seemed like a dead end. But Schwarz and Scherk realized that the theory's embarrassing prediction of a massless spin-2 particle, which had no place in strong force physics, was actually a gift. They proposed that string theory wasn't a theory of the strong force at all. It was a theory of everything, gravity included. And for years, almost nobody listened. Schwartz kept working on it, largely alone, through most of the late 1970s, convinced he was onto something even as the rest of the physics community moved on. Then, in 1984, Schwartz and Michael Green showed that string theory could be made mathematically consistent in a way that avoided certain fatal anomalies, and suddenly the whole field exploded. The so-called first superstring revolution brought hundreds of physicists into the subject almost overnight. But string theory comes with baggage. For the math to work, you need extra dimensions of space, not the 3 we experience, but 9 spatial dimensions, plus time. The extra 6 are supposed to be curled up so small that we can't detect them, compactified into tiny geometric shapes called Calabi-Yau manifolds. And the way those extra dimensions are curled up determines the physics we observe, which particles exist, what their masses are, how the forces behave. The problem is that there are an enormous number of ways to curl up those extra dimensions. Not just a few, not thousands, something like 10 to the 500 different possibilities. Each one gives you a different version of low-energy physics, and nobody knows how to pick the right one, or even if there is a right one. Some string theorists have embraced this as the landscape, a vast space of possible universes, of which ours is just one. Others find this deeply unsatisfying, because a theory that can accommodate almost anything predicts almost nothing. Now, the other major approach is loop quantum gravity, and it takes a completely different philosophy. Instead of starting with strings and discovering gravity, loop quantum gravity starts with general relativity and tries to quantize it directly, using techniques inspired by the gauge theories that worked so well for the other forces. The key insight, developed primarily by Abhay Ashtekar in 1986 and then extended by Carlo Rovelli and Lee Smolin in the late 1980s and 1990s, is that you can reformulate general relativity in terms of variables that look like the gauge connections used in Yang-Mills theory. And when you quantize these variables, something remarkable happens. Space itself becomes discrete. It's not smooth and continuous like the space of everyday experience. At the Planck scale, space is made of tiny, discrete chunks, quanta of geometry. Area and volume come in minimum units, just like energy comes in quanta in ordinary quantum mechanics. The fabric of space, in this picture, is more like a chainmail mesh than a smooth sheet, woven from loops of gravitational field lines, hence the name. Loop quantum gravity has its own elegance. It doesn't need extra dimensions. It doesn't need strings. It works in the 4 dimensions we actually observe. And it makes some concrete predictions, for instance, that the Big Bang singularity might be resolved replaced by a big bounce where a previously contracting universe reached a minimum size and then expanded again. But it has its own problems too. It's been very difficult to show that the theory reproduces general relativity in the large-scale limit, where we know general relativity works, and incorporating the other forces and particles of the standard model into the framework has proven enormously challenging. So here we are, two major approaches, decades of work by some of the smartest people who've ever lived, and no definitive answer. And honestly, that's okay. That's how science works. We're asking what might be the hardest question human beings have ever posed. What is the fundamental nature of space, time, and matter at the deepest possible level? It would be strange if the answer came easily. And you know what's remarkable? Even without a theory of quantum gravity, look at how far we've come. Think about the journey we've taken tonight. We started with Democritus 2,400 years ago, sitting in ancient Greece and proposing that matter is made of indivisible atoms, a pure thought experiment, no evidence, just a philosophical intuition that the world must have some fundamental building blocks. And from there, slowly, painfully, brilliantly, one generation building on the last, we figured it out. Dalton weighed chemicals and found fixed ratios. Thomson discovered the electron. Rutherford fired alpha particles at gold foil and found the nucleus. Bohr built his rickety model of the atom with quantized orbits, knowing it was wrong, but knowing it was on to something. Heisenberg threw out the idea of orbits entirely and replaced them with matrices. Schrödinger wrote down his wave equation. Born realized the wave was a probability wave. Dirac unified quantum mechanics with relativity and predicted antimatter before anyone had ever seen it. And then the quantum field theory revolution, Feynman and his diagrams, renormalization taming the infinities, gauge symmetry revealing the deep structure of all the forces, the Higgs mechanism giving mass to the particles that needed it. And finally, in 2012, the discovery of the Higgs boson, confirming the last prediction of the Standard Model. That's an extraordinary story, and every piece of it is encoded in the world around you right now. The phone on your nightstand works because of quantum mechanics. Its transistors rely on the behavior of electrons in semiconductors, behavior that only makes sense if you understand wave, functions, and energy bands. The starlight that traveled billions of years to reach your window is carried by photons described perfectly by QED. The nuclear reactions powering the sun, keeping you warm, keeping you alive, those are governed by the weak force and the strong force, by W bosons and gluons doing their work deep inside atomic nuclei. The atoms in your body, the carbon, the oxygen, the iron in your blood, were forged in the cores of ancient stars that exploded billions of years ago. And the physics of those explosions is the physics we've been talking about all night. made of quarks and electrons bound together by forces that took a century of human genius to comprehend, lying here in the dark, listening to the story of how it all works. And the story isn't finished. There's dark matter out there, something that has gravitational effects on galaxies but doesn't interact with light, and we don't know what it is. There's dark energy, something causing the expansion of the universe to accelerate, and we really don't know what that is. Neutrinos have mass, and the Standard Model in its original form said they shouldn't. So something beyond the Standard Model is going on there too, and gravity is still out there, waiting to be woven into the quantum tapestry. But tonight, you don't need to solve those problems. Nobody does. Not tonight. Tonight, it's enough to know that the universe is comprehensible, that atoms are real, that forces have structure, that symmetry is the deepest language nature speaks, that a handful of equations discovered by real people with real lives and real struggles can describe the behavior of everything from the smallest quark to the largest galaxy. That's not just impressive, that's kind of miraculous when you think about it. So let that settle over you. The particles that make up your body are gently vibrating, held in place by electromagnetic forces, governed by rules that Schrödinger and Dirac and Feynman helped us understand. The atoms in the pillow under your head are mostly empty space. Remember Rutherford's gold foil, held in their solid shape by quantum mechanical effects, by the Pauli exclusion principle, preventing electrons from collapsing into the same state. You are a quantum mechanical object, whether you feel like one or not. And right now, all those countless particles are doing exactly what the laws of physics say they should, including the ones in your brain that are slowly, gently letting you drift toward sleep. The universe has been running these calculations for 13.8 billion years. It doesn't need your help tonight. It's got this. So close your eyes, if you haven't already, and let it carry you.